Matthias, your mission, should you choose to accept it, is to take these photographs. A single frame, captured from orbit, of Houston and Zurich. To accomplish this, you must design, build, and launch a fully operational CubeSat. Power systems, avionics, attitude control, cameras, radios, antennas, all inside a box the size of a coffee mug. As always, should your satellite fail to deploy, mispoint, brown out, tumble, or burn up on re-entry, the Secretary will disavow any knowledge of your actions. Good luck, Matthias.
Well, okay then. So the mission is simple. Put an autonomous camera into low Earth orbit, snap pictures at specified locations, and beam them down somehow. Because neither USB cables nor flashcards are particularly practical at 400 km altitude. Physics and the CubeSat form factor give us a set of constraints. These are not negotiable. These are the rules of the mission, and we will need to design for them. Constraint number 1. Everything must fit inside a 10 cm cube. A coffee mug, essentially. That's the entire spacecraft. I had to build a mock-up just to wrap my mind around the tiny size and the problems this will cause. Constraint number 2. Power. There's almost no room for batteries, and only a few square centimeters for solar cells. Every watt matters. Here the yellow stickies mock up the solar cells with 2 per panel. Constraint number 3 is orbital speed. In this background clip, the International Space Station is just crossing from the Atlantic Ocean into France. The ISS is a good proxy for the movement of my CubeSat, which will be in a similar orbit. It will stream over Houston in about 30 seconds. That's the entire shooting window we have. Constraint number 4 are orbital tracks. Each orbit shifts by about 2,000 kilometers. We don't get to pick our passes. We need to plan around them. Orbits roughly repeat every 3 days, and half of them are always in the dark. Constraint number 5 is geometry. Cameras and downlink antennas must point toward Earth. GPS and SATCOM antennas must point at space, where the higher orbital satellites live. You can't have everything facing everywhere. We need to measure and control the orientation of our satellite. Constraint number 7 is temperature. The outside swings from freezing darkness to sun-baked heat. The inside has to survive both. While we can choose robust electronics, we will need to protect the batteries from the cold to ensure peak performance. These constraints map directly to requirements. Given the rules of the mission, my CubeSat needs 5 major capability areas: avionics, cameras, communication, power management, and structure. The first 4 map directly onto the CubeStack, my computer hardware consisting of 4 customized boards. The structure is the frame that holds them, points them, and keeps them alive. The avionics board is the brain. It keeps time, knows where the satellite is, and predicts where it will be going. It senses orientation, actively detumbles and orients the spacecraft, and decides when to take the shot. The payload board is the eyes of the mission. It drives the cameras and sensors, handles exposure and readouts, and buffers the images. Each one 5 to 10 megabytes in size. The communication board is the voice. It handles the internal CAN bus, the RF downlink for telemetry, and optionally a satellite modem that addresses the communication bottleneck of getting a 10 megabyte image back to Earth, or much more if we capture bursts of multiple cameras. The communication board is also the ear. It receives commands and must be able to flash firmwares. The power board is the heart. It captures solar energy, charges the batteries, regulates every power rail, and enforces the power budget by switching other boards and functions on and off. If this board fails, the mission is over. Thus it needs redundancy to keep the satellite and its mission alive. And finally we have the structure, the body. It's the frame that holds everything, aligns the cameras and antennas, and survives deployment, including the tremendous launch vibrations and the severe thermal cycling in orbit. It's the one part that has to obey every constraint. We commented earlier that we were essentially getting a camera, or more accurately, a smartphone into space. Many of the requirements ultimately require software solutions and integrated hardware. For all of this, I'm sticking to the STM32 universe. Not because it's trendy or easy, but because it's a robust ecosystem that I've used for years. Boards like the Blue Pill, Black Pill, WeAct, WaveShare, the SpeedyBee flight controllers, my own boards. And microcontroller families like the F1, F4, H7, and of course the L4 that are mostly interchangeable. I've built with all of them. The toolchains are stable, the compilers are standards, and the development environment is robust and offers a hardware abstraction layer and bare metal access where needed. And when you run something that is going into the space, supply chain, familiarity, and interchangeability are features, not options.
This concludes the mission briefing. Now like, subscribe and comment below to request further briefings on boards and project aspects, should you decide to do so.
I could not have said it better. Thanks for joining 4111 Spyglass Mission Control. See you next week.